Greetings. Welcome to Calculus in the PM. I'm your host, Mr. Sudelica. It's coming to you live, recorded. Fundamental theorem of calculus part 2 is what we're going to look at today. And it's also called the integral evaluation theorem, but fundamental theorem. Anyways, as long as the function is continuous inside an interval from a to b, and the antiderivative, use a capital F, of the original function inside there, it exists, say you have an antiderivative, then you're going from a to b, so from 2 to 3 for that function. You can evaluate this area, or this integral, I guess, knowing, take the antiderivative with b plugged into it minus the antiderivative with a. So top minus the bottom when you plug it into the antiderivative. Yes?
How is this different than what we were doing in 6.3?
It's all related. And we actually were doing it in 6.3. We just didn't have the theorem as such. Yeah. So this is really more of the same thing. So this means as long as you can find an antiderivative for a function, you can evaluate an integral without Riemann sums, which take a long time and aren't very accurate if you're doing them all by hand. Sometimes that's the best you can do, especially if you have chart data from a real science experiment or something. Anywho, without Riemann sums. If you have to complete an integral without a calculator, this is usually the best way. Obviously, if you have access to a calculator, that's not during the test, though. The calculator is the best way, if you can enter it correctly. By the way, on this, and I'll tell you which questions are which. When you write this test, there will be a portion that I'll say is no calculator, and then a portion that is calculated. You'll have two parts. Because your calculator can evaluate all of these things, and I want to see that you can do it without as well. So let's try this one. Evaluate the integral from -1 to 3 for this function, 3x squared plus 1, using an antiderivative. Now, I don't need the picture, but as soon as I see 3x squared plus 1, I hope you're thinking like this. That looks like 3x squared plus 1, and I'm really finding the area, -1 to about 3. This is not drawn to any scale, but I'm finding the area from a line, x equals -1, x equals 3. I'm finding the area that I just boxed in with the x-axis, right? So that's really what I'm finding there. Okay. Now I say the word area, and I'm not being too careful. This happens to be a positive area. If it was below the axis, it would come out to be a negative value, right? The integral. So that's what that represents, and, well, let's just get to it. So this question here, -1 to 3, 3x squared plus 1. And you're doing this integral with respect to x. So you ask yourself, what is the simplest antiderivative of this expression? Well, the 3x squared part. It would have come from something with an x cubed in it, right? So I'm going to write down, I'm going to put a square bracket here, something with an x cubed in it. Now remember that if I just wanted x squared, I would have had 1/3 x cubed, right? If you take the derivative of x cubed, what do you get? Do you guys see that? That's the antiderivative right there. Okay, I got that hitched up there. I'll just scooch that in a bit more. X cubed plus, to get 1, the derivative of x is 1. Okay. And I'm going from -1 to 3. So I've done the antiderivative. And now it's numerical evaluation after this. So this is equal to, I plug in the 3. So 3 cubed. I'll write it down as 3 cubed. Plus 3. Subtracting -1. It's important you use brackets when you have these guys like this. Because it's arithmetic, and the most common error I see with arithmetic is SIGN, sign errors. So 27 plus 3. I make a lot of arithmetic mistakes, so watch out, tell me. -1 cubed is still -1, plus another -1, so minus -2. 32 is this area. Okay? No, scanning and I didn't make any mistakes. So the numerical area, 32. Okay. And you could see this application probably in physics and stuff like this. If you, I know you guys are talking distance time and stuff like this. If you have accelerated motion, you will have a quadratic portion. And to find displacement, if you have that as a velocity that's accelerating, right, it's changing, so on, and it's changing with a square. Now, you guys, in physics, you guys keep it to constant acceleration, so you'll always get velocity graphs that are lines, right? But you might have a situation, a more realistic one, where it's a curve. You'd use calculus and so on to find those areas, so you'll never do it in high school. Anyways, evaluate the next one. -1 through 3 for 1 over x squared, using an antiderivative. Okay. So, I'm asking you guys, what's the first thing? Do you like operating like this? No? What do you do?
X and -2.
Okay.
This function isn't continuous on the
Good. He saved you guys a bit of work. I was going to say, okay, you can actually get an answer for this, but it won't be a valid answer. What did he say? Somebody else? What did he say? Not why not? The zero. Aha. Some people are paying attention. 1 over x squared, what does that look like? Looks like a volcano or something, eh? Even if you don't know what it looks like, the x squared portion makes sure that it's always positive. You should scan quickly if it's not a polynomial. Polynomials are are continuous. As soon as you have a rational, or possibly with an even root, you know that you know your domain is going to be affected. And that is where x can't be 0. Is our domain restriction. You would not get a valid area. And the reason being is that goes up forever, right? How can you compute that area? So, it doesn't work here. You can't do this. I would have stopped after one step, but if I could evaluate this if that was positive 1 to 3, though, right? But it wasn't. And if it was positive 1 to 3, you would have probably thought of that as x to the -2 dx. Add 1 to that, x to the -1, and think, okay, what would okay, negative, and then go from there, okay? So make sure it's continuous. Even if you don't know what the picture of the graph looks like, as long as you know there's a domain restriction and it's included in the interval from -1 to 3, for example, you can't do it.
Did you just say it was infinity?
We'll just say undefined. Okay, yeah, I guess I haven't said anything. This is undefined. Because, well, you just say, yeah, it's, I'll just stick with undefined for that. I wouldn't mark you wrong if you said infinite. Because, yeah. Finding area using antiderivatives. Now, we're keeping in mind, if you're asked for area, you typically need to have a positive answer. If you're just evaluating the integral, it's positive or negative. The integral could mean area, depending on the context. Now, section 5.2, did I not change 6.2? The old textbook said 5.2. Anyways, we saw that the definite integral can be interpreted as the net area between the graph and the x-axis. We can therefore compute areas using antiderivatives. But be careful not to distinguish between net area, in which the area below the x-axis is counted as negative. And we don't usually use the word net area. Just if you see the integral sign, just do it. That's typically going to be positive or negative wherever it goes. And it's different, though, if you're asked for a total area, the absolute value of the area added together. Okay? Use context to see if you need net or total area. When you see the word area, though, in this textbook, and most others, think of it as total area. Find the area. They're going to say, make them all positive. So let's see the difference between here. Find the area of the region between the curve, y equals x squared minus 9, and the x-axis in the interval 2 to 4. You can use absolute value around the function on your calculator to check answers, but I want you to first, we'll do this by hand. So, sketching the graph, x squared minus 9, I hope you all realize is a parabola, zip down to minus 9. I'm not being perfect here, just something like this. Now, I'm going to get a little more curve to mine just so that it fits in better, but that's all. Not more curve, but I want to cover more left, right. Okay, and then from 2 to 4, x squared minus 9, where's my 0 on that x squared minus 9? 3. 3 squared minus 9. So if this is 3 here, going up to 4 and 2. Okay. There's my 1. Okay. I want the area. You can see that it'll include this negative portion. It'll include this positive portion, right? So the net area and the total area will be two different things. Total area is easier to, the net area is easier to find. Sorry. For the net area, you just do the integral from 2 to 4, x squared minus 9, dx. If it comes up positive or negative, so be it, because it's adding the negative area plus the positive area, finding what you get. So when we do this, x squared came from 1/3 x cubed minus 9x. That's the simplest antiderivative I could think of. You could have had plus 5, but I won't change it at the end. Okay, and then you just do arithmetic. Now, you won't get a ton of arithmetic to do on AP tests, like where it's crazy denominators. You'll typically have nice fractions, generally out of 12 and stuff like that. Let's just go with this one here, though. We'll do the arithmetic. 4 cubed divided by 3. So 4 times 4 is 16 times 4 is 64 out of 3. Minus 9 times 4, 36. That's only the first one. Then the whole thing there subtracted from 2 plugged into here. 2 cubed is 8, so 8/3 minus 9 times 2, 18. Now, what you might be tempted to do, and sometimes it's a good thing to do, is to make everything out of 3, the 16 and the 18. You could do that. However, you could also think of these as sort of like terms. Group my integers and group my fractions, and then go through that. It's a little less work, I find. So let's see here. 64 subtract 8 out of 3 is the 56 out of 3. Now, negative 36 minus negative, so add 18 to negative 36, and that's 18 again. Now, when I do it that way, I'll still get the same final answer, 56 out of 3. Is 56 divisible by 3? Unfortunately, it's not. So then you gotta come up with 18 times 3, pardon me. Isn't that 54? Yeah, 54. So 56 minus 54 out of 3, that's what the 18 is, 2 out of 3. If you need to write more steps in there, go ahead. 2/3. So it has more positive area than it has negative area, too, that means, right? Now, because my drawing wasn't careful, it kind of looked like that, but I did not sketch it carefully, so you might not have predicted that. Finding the total area, though, this one's a bummer. Because what you got to do is do 2 to 3 as an integral, and reverse the sign on it. Add that to 3 to 4. Okay? So there's no way around it, it's just more work. So what I do is, from 2 to 3, I'm going to have the opposite sign. Why? Because I know that's below the axis. So that means you have to know something about the graph of this. X squared minus 9 dx added to, so that first thing will actually come out now to be a positive answer, right? Added to from, 3 to 4. Oh, I better put the integral, the snake. Now we know the antiderivative, we thought about it before. X squared, did I make a mistake yet? Oh, that thing. Every time I use the eraser, it's a 50-50 thing whether or not that computer glitch there. Thank you. Okay. I thought maybe my hair was on place or something. Okay, anyways, negative. What are we getting here? X squared, or the antiderivative, 1/3 x cubed. Oh, I don't know if that's going to disappear or not. 1/3 x cubed minus 9x. And you're doing it from 2 to 3. Added to the area. 1/3 x cubed minus 9x. 3 to 4. So there's far more arithmetic here. And that sucks. Tell you what, trust me on this one. Or maybe you shouldn't.
No.
Yeah, that's just cool. Okay. I'm going to keep this negative sign outside. And then, with the 3 plugged in, we get 3, I'm tempted to, 27 divided by 3, which is 9. 9 times 3 is 27. Oh my goodness, I can't squeeze this in here. Subtract 8 over 3. Where am I? 18. Where my head shuts down. Now, I can do this, you can't. I'm going to just scooch this stuff sideways because I need the space. Oh. And, well, you know how the arithmetic works. Then we add the other thing. I plug the 4 into there. I get 64 over 3. We knew that from before. Minus 36. Subtract. And then we get our negative 8/3 again. Yep. No, I mean 9 minus 27. Okay. Yowzers, eh? Doesn't this suck? Is what you're thinking. So, depending on how you want to do the arithmetic, you could drag, and you could have done this before, the negative sign through this whole system, right? And then you can group the whole number, or the integers and stuff like this. I think I'm going to approach it that way just to be a little more careful. So 9 minus 27 is negative 18. Negative 18 switched with signs is plus 18. Now, that's from the first bracket when I drag the negative sign through here. Watch me, though. Make sure I don't make a mistake. And then, I'm applying the negative sign to this. Now I apply the negative sign to that, subtract, and that turns it to adding, right? So plus 8/3, and you see that it's going to happen, minus 18. That's the first bracket. Plus 64 out of 3. I'll keep this minus 36 for the moment. Not do too much at once. Minus 9 minus 27. So minus negative 18 is adding 18. Agreed? Don't just trust me, because I'm bound to have made an error. If I haven't already, I will soon. Now, 18 minus 18. Okay, that's nice. So I got the 36, negative 36 and 18 to group. So negative 36 and 18, negative 18. Is that right? Okay. Then, 64 out of 3 plus 8 out of 3, 72 out of 3. Yep. Now, what's 72 out of 3? Well, just think it through. You can do it without a calculator. I'm asking you to. You can even think of it as goes into 7. 24. 3 groups of 25 is 75 is the way I think. So 24 groups. Okay. So this is, I'm going to write it sideways. I wouldn't normally, but I'm running out of space. Negative 18 plus 24, 6. That's the total area. Now, I didn't find, mathematically, I didn't do the arithmetic to find the area of each region. I could have. I just combined them together. Okay. If you wanted to just find the area that's under the x-axis, you would have just done that arithmetic right there, right? Anyways, and then vice versa for the above the axis. There's a heck of a lot more work if you had to find total area. That's the lesson learned here. Now, one other thing, and this gets goofy. What if, and we've seen a function like this, what if a function is something like this? It has an integral in it. So g of x is from 0 to whatever your x value is, the integral of that function. And here's my function, piecewise function. Straight line, some kind of curve, we'll do some estimation, so on. From 0 to x. Now, we've got to think about what this function means. If I plug in 0 in for x, so I'm saying I'm finding what's g of 0, that would mean I'm doing the integral from 0 to 0. What's that going to mean? That is 0. That's the easiest one to find. Then I plug in 1. So when x is 1, I get the integral from 0 to 1. I am finding this area right there of the triangle, right? 1/2 base times height, so 1/2 times 1 times 2. So the area is 1. I can also jot that in here. This is 1. Okay. Then the second area, or when x equals 2. Now, if I've got 2 there, that means I'm finding the area between 0 and 2. I'm finding all of this. Luckily, and this is why I jotted down the 1 there, we've got the triangle figured out, plus, you can see it's an area, the rectangle is 2. So added together, that's 3. It accumulates. Now, you'll notice I have wavy lines. So these are approximations. We'll just approximate, okay? Yep. Yeah, I should have put 3 there. Thank you so much. I said it and didn't write it. And I had disappearing anchors when I didn't want it. So 2. 1 plus 2 is 3. Thank you. Now, looking at this area here, we could approximate it with a triangle, right? Doesn't it look like, because it's sort of concave down, that the, and I'll emphasize this curve, it'll be a little over the area of that triangle. So it's a little over 1. Let's go with 1.2. This is an estimate. Now, I'm going to guess, and this is why it's approximate, right? So it's the area from 0 all the way up to 3 here. I'm saying 1.2 for that area, so 4.2 total area. And that's where the 3 is, right?
That meant like G of 4 is 3, is that negative 1?
Oh, yeah. G of 4 is 3, because I'm assuming this looks not exactly symmetrical. It looks similar, but twirled around 180 degrees. So this is a negative 1.2 for this portion here. And that's what you're saying. So negative 1.2 plus the 1.2 plus 1 plus 2. 3. And another negative 1.2 then. In this last zone. Thinking about that, I just add 1.2. Negative 1.2 I add to 3. And negative 1.8. Because we know that the previous areas all added up to 3. Subtract 1.2 from that, 1.8. Okay. Then sketch a rough graph of that function. So let's just think this through here. Now 0 and 0, I have it there. And 1 is 1. And this is very rough. Oh, do that. I'm going to lock this in place so don't accidentally move it more. Okay, so 1-ish. 2, I go to 3. 3, I go to 4.2. I couldn't see that. Yeah, that's 4.2. So 4.2, 3, 4, a little more. And then the number 3 again for 4. And 1.8, lastly. So a little lower than where I think 2 is. I'm standing this close to the board, I have a hard time estimating from a distance. It would probably look better. Now this, I think this looks like a curve. Now this is an approximation. So. I couldn't see through the shadow there at the end with that little shape. That's kind of what, this is approximately. Try the other questions there. Now that